Reinforced concrete beam T-shaped section analysis. In this video, we review a section which is a T-shaped section. So this is a T section. And the very first step to and also T-shaped section is very similar to double reinforced concrete section. The very first step in analyzing a T section is to first develop a simple rectangular section with the tensile steel at the bottom of the section with the height of D effective and height of B of flange. And then we just consider first we calculate the depth of A. So by developing this rectangle, we calculate the normal height of weakness block, and then A is area of steel times yield strength of steel over 85% of F prime C times B, which is the dimension to the bore. And then the second part is make a comparison between A and height of flange. If A is if height of weakness block is less than HF, we are not entering to the web of a T section, and we do not need to. If A height of weakness block is less than height of flange, there is no need for T shape section analysis. So you can just go for a bit a rectangular cross section. But if A is higher than height of flange, it means we already enter to the domain of web, and T-shaped section analysis is we need to do the analysis for T-shaped section. So let's consider the forces on a T-shaped section. So if you just consider a T-shaped section, it's very similar to the tensile, a double reinforced kind section. So double reinforced concrete sections is a very similar to T-shaped section in a sense that we can dissect. If you remember, in double reinforced section, we just dissect the section to a domain of compression steel and domain of tensile steel. So this time we can assume that these two extra part at flange, they just work like assume like we have a compressive concrete steel at the top. So these two extra part, just we can just simulate them with a, a make a comparison with a tensile compression steel at the top. There is no steel there, but just imaginary steel. So we can dissect the forces in this case into two. So one of them is 85 percentile of F prime C, B minus BW. So if we just subtract bits of web, we can just go for these two part, and we can simulate that like a compression domain forces. And the other part is definitely 85% height of Whitney blocks, which is the other part, and that just goes by a height of Whitney's block times width of BW, 85% of prime C times A times BW. And in that case, we can just dissect the total a steel force like AS times Fy and just like double reinforced, we call that AS2 Fy plus AS1 Fy. This time it just says total a force of tensile is goes area of steel related to flange times Fy plus AS minus AS flange times Fy. So if you just consider it once, you need to subtract it from the tensile steel. Do not consider it two times. So by having that, can have a moment. So MRF also, we call that MN or MRMN is nominal, identical to each other. Nominal moment or persistent moment of a section, and that any moment, any kind of moment is just a force times its arm. So the force is a area times a stress, and this is the arm. So for example, MRF, MNF is a resistant or nominal moment related to flange, and that's definitely area of steel related to flange. Imagine just you can assign that to place these two parts, be it a tensile, compression, steel. There is no steel there, but you can assume that like AS related to flange and times Fy can just replace these two parts by a, assume that's like ASF times Fy times D minus HF. So that force is applied at the, so let's put it this way. If there is a force like there, that's applied to HF over 2 because that's related to flange. So that's the R here. And that's equal to 85. So if the section is in a static mode, summation of forces in x direction goes 0. This force should be equal to this force. Then their arm is also the same. So you can cancel out the arm. And the forces should be equal to each other, and that's equal to 85 percentile F prime C times a minus BW HF. So the only unknown in this equation is ASF, and if you just solve the equation for ASF, it just gives you area of a steel related to flange, and by having that you can easily go for MNW RS resistant moment for web, and that's definitely as soon as you have ASF, you can replace it in this equation. That gives you AS minus ASF, like in double reinforced concrete, AS minus AS or AS prime times Fy. This time my arm is A over 2, A over 2. Height of witness block is A, and this time I'm just going by A over 2 because the force applies at the A over 2 for the height of A. So that's A over 2 times, and then that's equal to 85 percentile of F prime C times A times BW E minus A over 2. Here again, the only unknown also is my only unknown here is A. And if you solve the equation for A, it just gives you a new A, and that's A equal to height of witness block is AS minus AS flange times Fy, and that's the exact A. Then if you add up those two moments, then you have, when you know what your AS F is, When your A is, you can calculate M, NF, MRF, MRW, add them up together and you report it like a resistant. And also you can write it like this: Mn is equal to Mn for flange plus Mn for the. That's exactly this equation. They are identical to each other. We'll solve an example which apply in a practical engineering problem.